Welcome to the first part of the problem-solving session for Chapter 36. Let's begin with question 1. Here, we're asked the following. If a clock is held in front of a mirror and its image is reversed right to left, from the point of view of the person looking into the mirror, how does the image of the second hand rotate? Is it clockwise or counterclockwise? In fact, it is counterclockwise because right is reversed to left and clockwise is reversed to counterclockwise. Next question. Which kind of mirror, concave or convex, can be used to start a fire with sunlight? Well, it's concave because in the case of the concave mirror, if you recall, let's draw our principal axis. All rays which are, and here's our focus and the center, all rays which are parallel to the principal axis strike the mirror and converge at the focus. So all these rays coming in parallel would focus at the focus, and so here you might put some piece of paper or wood or chippings to start the fire. When you look at the back side of a shiny spoon held at arm's length, you see yourself upright. Why? Well, because the back side of the spoon is a convex mirror, and convex mirrors always produce virtual images, which are upright and reduced. Upright's got a T. Okay. When you look at the other side of the spoon, you see yourself upside down. Why? Because now you're looking at a concave mirror. The properties of the image are, if you're sufficiently far away, real image, inverted, and if you're sufficiently far away, reduced as well. Next question. Sometimes news personnel covering an event use a microphone arrangement that is designed to increase the ability of the microphone to pick up weak sounds. The drawing shows such an arrangement. How does this enable the detection of weak sounds? Well, what you can see here is that all sound waves which are going to strike this semi-spherical or even parabolic arrangement are going to reflect through the focus, and of course through the focus is at the location of the microphone, and so this enhances the detectability of the sound waves. Next question. Suppose a spherical mirror has a focal length of plus 10 centimeters. Well, that tells us that it's going to be a concave mirror since it has a positive focal length. Use the mirror and magnification equations as well as ray diagrams when possible to describe the image that is formed of an object that is placed at the following distances from the mirror. So we've got P equals 25 centimeters, P equals 10 centimeters, P equals 5 centimeters. Well, let's go ahead first and use the mirror equations and magnification equations, then we can draw our ray diagrams. Well, the first case is where P is equal to 25 centimeters. Here, using the equation 1 over F equals 1 over P plus 1 over Q, we solve for Q, or rather 1 over Q, equals 1 over F, in other words 1 over positive 10, minus 1 over P, P is 25 centimeters. Let's see, if we choose the common denominator of 50, you can see we get 5 minus 2, which is equal to 3 over 50, and that means that Q is equal to 50 divided by 3, which works out to be about 16.7 centimeters when we round it. The magnification, so this tells us that the image is real. The magnification equation tells us that minus q over p gives us minus 16.7 divided by 25. This gives us minus 0.667. The minus here tells us that it's inverted. The 0.667 tells us that it's reduced. So we go ahead now and draw a ray diagram for this situation. We've got our concave mirror. We've got somewhere out here, if we extended it, the center of the mirror, the focus of the mirror. And if the focal length is 10, the radius is 20, and our object is someplace over here. So this is our object. And we have first principal ray, I'll draw this in red, parallel to the principal axis and reflects through the focus. Second principal ray, let's do this in blue, passes through the focus and reflects parallel to the principal axis. Third principal ray passes through the center and reflects back through the center. And so what you can see here is, let's go back to green, that the intersection of all the reflected rays, those are the ones we're interested in, determines the location of the image. And sure enough, as you can see, this arrow is upside down. The tail of the arrow must always be, whether it's an object or an image, at the principal axis. But you can see it's inverted, it's upside down, it's reduced, it's not as tall as our object was, and it's real because it's in front of the mirror. In part B, we're told that P is equal to 10 centimeters. Using the mirror equation, 1 over Q equals 1 over F. Well, 1 over F is 1 over positive 10 minus 1 over P, which is minus 1 over 10. Well, that gives us 1 over 10 minus 1 over 10 gives us a value of 1 over Q, which is equal to 0. Well, that implies that Q is equal to infinity, something very large. Well, this right here tells us we stop and go no further. We can't get a magnification for something that's infinitely large, and we certainly can't draw a ray diagram for this situation. So no diagram available, no more information can be obtained because the image is so far away that we're unable to find the rays that intersect with each other to be able to form the image. Last, P is equal to 5 centimeters. Here, mirror equation, 1 over Q equals 1 over 10 minus 1 over 5. We find our common denominator as 10. 1 minus 2 equals minus 1 over 10, which implies that Q is equal to minus 10. Well, that tells us, and by the way, the unit here is centimeter, this tells us, because of the negative sign, this tells us that it's a virtual image. M equals minus Q, well, Q is negative, so minus 10, divided by P, which is 5, tells us that the magnification is plus 2. Well, the positive sign tells us that it's upright. The number 2 tells us that it's enlarged. So if we had to draw such a diagram, well, let's see. We put our mirror here, and here again, the center of our mirror, the focus, and of course the focus is 10, so we need an object which is inside of the focal length, and there it is. First principal ray in red, parallel to the principal axis, and reflects through the focus. Now, because we know that our image is virtual, we need to also, we know that the image is going to form behind the mirror, we need to back trace our reflected ray. Second principal ray starts as though it's coming from the focus, so we orient it as though it was in line with the focus, and reflects parallel to the principal axis. Well, here again, we know the reflection will form in the back of the mirror, so we back trace that ray. Third one comes in as though through the center, well, through the center is in this direction here, reflects back through the center. Here again, we back trace it through the center, and here is our image. Our image is at the intersection of the back traced rays. It is upright, as you can see, it is enlarged, and it is virtual. Next question. Suppose a spherical mirror has a focal length which is negative 0.25 centimeters. Use the mirror and the magnification equations as well as ray diagrams to describe the image which is formed when the object is at 3 centimeters in the front, from the front of the mirror. So F here is minus 0.25, and this of course tells us that it's a convex mirror because of that negative sign. So first we want to obtain the location of the image. 1 over Q equals 1 over F, but of course F is negative, so I'm going to put my negative sign right there. 0.25 minus 1 over P, or 1 minus 1 over 3, and I'm going to go ahead and work out the number. Q is minus 0.23 centimeters. M, and of course that negative tells us that it is a virtual image. Well, we knew that because convex mirrors always form virtual images. Negative, or minus Q, Q is minus 0.23, divided by P, P is 3, we get M is equal to positive 0.0769. Well, this tells us the image is upright, and the number certainly tells us that it's going to be reduced, in fact, quite a bit reduced. Well, a ray diagram for this situation. Okay, here's our convex mirror. Here is our principal axis, and here is F for the mirror. Here is C for the mirror. My lines aren't very straight. But we'll do the best that we can here. We place the object someplace along here, in fact quite far away from the mirror, 3 centimeters. And we proceed to draw our principal rays. First one parallel to the principal axis and reflects as though it was coming from the focus. So back trace it to the focus, and out it goes in front of the mirror. Second one, through the focus, so it comes in as though it's going to pass through the focus, and then, okay, my line could have been a little higher there, and then reflects parallel to the principal axis. Well, we're going to back trace that, and there it is. Third one comes in as though it's going through the center and out through the center. We're going to back trace that. There it is. Okay, well, we don't have very good agreement here because I had trouble with my straight lines, but I'm going to fudge this just a little bit, and our image should be someplace, oh dear, should be someplace over here. Anyway, tiny as it may be. But this is where our image is located, and we can see that it's upright, it's reduced, and it is virtual. Well, this concludes the first part of the problem-solving session for Chapter 36. Until next time.